And so now we're going to hear from someone who will be presenting online. Ahmet Becene is I believe, an engineer with Collins Aerospace. And he's going to talk about heat transfer in nature. So you'll see that this afternoon is about very technical things. So we're going to sort of balance our big ideas and mindset shifts with the really important research and applications that need to be done to bring a new kind of transportation into our lives. So,
well, thank you everyone for joining. Today we're going to talk about something really interesting, something I'm very passionate about, how nature affects the engineering design in high-tech industries, in my industry being the aerospace. I'm going to start this talk with a question. I know there are a lot of smart people in that room today. And there are a lot of people watching it online. Let's say you're an engineer in thermodynamics division, and you have a structure that weighs about 15,000 pounds. And this structure needs to function in 120 Fahrenheit environments. For our metric friends, we're talking about something like 67 tons and about 50 degrees Celsius. And we have to circulate about 70 gallons of fluid in this system. And the end goal, the engineering criteria, is we need to reduce the temperature within the structure by 20% below the environment. So how do you accomplish this? If you were to take this question and give it to 10 different thermodynamics engineers, heat transfer engineers, you're going to get 10 different answers. That doesn't mean all 10 are wrong. They're all going to function. They're all going to serve a purpose, but none of them will be optimized in the true sense of the word. And if you look at what nature has done over millions of years of evolution, came up with this structure. An African elephant dissipates about 8 to 10% of its body heat using their ears. And if you were to look at the, let's say, design or evolution of the African elephant's ears, it's very fractal in nature. It's a two-dimensional structure. And the heat transfer is achieved by pumping the blood through the fractal bifurcations through the ear. And when the elephant flaps the ears, you dissipate about 8 to 10% of this 15,000 pounds of mass is internally generated heat, which is amazing. And you're still able to keep your body temperature 20% below the environment. So this was my inspiration on how to take a structure like this and apply it to a very high-tech industry, specifically military jet engines for the next generation. So today we're going to talk about that journey. Let's talk about optimization very quickly first. What is optimization? Now that's the word that gets thrown around all the time. It can be structural, it can be electrical, it can be thermodynamics, anything that is based on sealed quantities, anything that is solved by using differential equations can be optimized on paper. But what if you have to deal with so many different factors? Then what is the optimization? In general, if you are a mechanical engineer and you're dealing with structures that carry load, the most optimized structure would be uniform stress everywhere. So a column out of a Greek temple, circular in cross-section, constant cross-section, and always under compression, it's the best optimum structure for that particular application. Why? Because your sigma equals F over A, your stress is uniform everywhere. But nature doesn't work that way. And engineering structures don't work that way either. Why? Because loading is going to come in from infinite different coordinate systems. Loading is going to be time dependent, so it's not going to be constant. So now you have variations in time and space. That's a partial differential question. How are you going to minimize your material usage when the outcome, the success of your species is based on multiple factors? And that's where nature comes in. You're either minimizing an energy usage, such as, let's say, trees transporting nutrients, or you're maximizing surface area by minimizing material usage, like honeybees, or you're minimizing weight and material usage while maximizing strength, like bones in your skeletal system. That is the true definition of optimization. being able to satisfy multiple physical criteria by minimizing one or two or more functions. So it's no secret then, or no surprise, if you were to take an engineering structure, such as the one you see on the left, a load-bearing structure, and define your geometrical design space, and then define a few functions for the desirable outcome while minimizing a few functions such as volume or mass or overall strain energy density within the system, you're going to end up with things looking very biological. I started working with topology optimization about 20 years ago, and it fascinated me because whenever you solve these complicated partial differential equations based on multiple optimization criteria, everything ended up looking very, very organic. Back then, we did not make them. So a lot of the structures I designed, they went into folders. They look beautiful for presentations, but that wasn't something we could do. We could make and either put on the road or, put them in the air. Things are different today because we have additive manufacturing capabilities. So we can make things that are very unique in shape. So the structure that we design today looks very organic, purely based on mathematics, not based on millions of years of evolution, but they end up looking very much the same. And this is evident not at the macroscopic level, but also microscopic level. One type of structure that I'm absolutely fascinated with is called the diatoms. These diatoms are so tiny, human eyes cannot see them. But if you were to look at the structure itself, as a mechanical engineer, I'm looking at it from stress point of view, from fluid mechanics point of view, from thermodynamics point of view. These are truly optimized structures, either to minimize mass while maximizing strength, like here, or minimizing flow resistance so that they can extract the maximum amount of nutrition from the flowing fluid, like here, or doing both, like these two structures, while minimizing material usage, also minimizing the flow resistance through these structures. So fascinating. And if you were to take those physical quantities and put it in differential equations and then run it through an optimization program, you're going to end up with these. Now, nature is not Euler. Nature did not solve these differential equations, but it did end up with these solutions over millions of years of evolution and trial and error. Since the early days of my career, I've always focused on nature as the best engineer. And a lot of the inspiration that I'm putting in the designs or technologies I'm developing, Raytheon technologies, are coming from nature because of structures like this, as small as they might be. If you look at how engineers optimize things using mathematics versus how nature optimizes things using natural process, it's quite different. The way that we do it, you see it on the left here, is remove the material when it's not needed. The way that nature does it, add material as it is needed. Now, that might look a little wasteful from the engineer sense, but we're not using real material. These are mathematical functions. Everything is done in simulation. So we put an overall design space. Let's say this is a topological optimization scenario. And you put your constraints as the boundary conditions and loads, and the simulation starts. And what simulation does is looks at every single thousands and thousands of finite elements locally and their strain energies and strain energy densities. As they get closer to zero, they get removed, and this iteration happens again, and again. From 0 iteration to about 50 iterations or so, in general, you will end up with a structure like this. So this is subtractive. We've taken the material we don't need out. Nature is adding it in. The one on the left happens in matter of minutes on high-performance computers. What happens on the right happens in millions of years. Both of them end up with the same result. Nature doesn't have access to fast computers, so it's happening in trial and error. But we are ending up with very organic-looking structures coming from both sensitive views. We don't have mathematical functions to add material. So the way that I look at it is your mathematical sculptures. We get rid of the material as we don't need it. We chisel it away. And then what we end up with is the optimal structure for that particular application. Nature does it differently. It builds up because it cannot afford to start with a big block of material and chisel it away. It has to start with the absolute minimum and then add as it's needed. Otherwise, your species will go extinct. So now let's get the fractals, because it's going to be based off our talks. What is a fractal? They're fascinating geometrical patterns. It never ends. You can keep zooming in and zooming in. You're going to see that they're going to repeat themselves. Even though they're super complicated, as far as the human eye can see, they're created with very, very simple mathematical equations. And then they exist in familiar dimensions. When I was getting my doctorate at the University of Rochester, I took a course called Chaos Mathematics. And in that, we talked about fractals quite a bit and the dimensions of the fractals, which boggle my mind. Because if you were to look at this fractal here, this is a cofractal. It's a two-dimensional line, but it goes forever, which means you can put an infinite length of curve length into a finite amount of space, like a piece of paper. So now you have something that is higher than one-dimensional or less than two-dimensional. If you were to look at two-dimensional fractals, their dimensions actually is going to be higher than 2 and less than 3. So these are fractional dimensions that fit in between the dimensions of real use, so like 0.0 being a dimension, or line being one dimension, or surface being 2 dimensions, and familiar space we live in is at 3 dimensions. So these are 1.5 dimensions, 2.5, 2.7, very interesting structures. So how do you take this and apply it to nature? Or, well, nature applies it itself, but how do you take this and learn from nature and apply it to engineering structures? I started working on this about 10 to 12 years ago, once additive manufacturing became feasible in the industry. Because structure like this, you won't be able to manufacture using subtractive machining techniques. You have to use additive machining techniques, just like nature. So if you start looking what fractals look like in animals, here we're looking at a lung system out of a mammal, looks like human lung system. We are transporting a fluid. It could be air, it could be blood, it could be nutrients, it could be waste, right? It could be air, gas in nature, it could be fluid, or it could be solid. While we do this, there are things that we need to minimize. Minimize the material that makes up the structure, minimize the energy consumption that structure will need to use to function, and also maximize something. It's not just always minimizing. You have to maximize something. And in this case, for the lungs, you're maximizing your surface area. So you have a finite volume that is going to fit in your body. Your body cannot be infinite in size. To maximize the surface area for maximum oxygen transfer. In that case, here we're dealing with a structure that is bifurcating to ever decreasing size fractals. In human lungs, the fractal order, how many times it bifurcates, is fairly small. It's something like 6 to 7 to 8. But the surface area increases dramatically. In fact, if you were to take the surface area of human lungs and open it up to a 2-dimensional sheet, it's going to be about half the size of a tennis court, which is incredible considering that it's the size of a party balloon. If you were to use a party balloon and open it up to a 2-dimensional surface, obviously you're not going to be as near as a half of a tennis court. So this is a perfect example of how fractals are used in nature to maximize something while minimizing something else. Applies to trees as well. Anything that's plant-based is actually using fractals for shape itself. Here you're trying to maximize your nutrition transport while also maximizing your surface area at the end of it so that you can get maximum amount of solar energy. But you also have to minimize mass. You also have to minimize your center of gravity being closer to the ground, and you also minimize your bending moments. which means as you are going up in the tree structure, you need to reduce your volumetric density, which means your local area density and local area weight per volume is going to be less, but you have to maximize your surface area. So you're going from a three-dimensional topology to a two-dimensional topology while maximizing the two-dimensional topology by minimizing the three-dimensional topology, which is amazing. And you achieve that using fractals. It doesn't just apply to biological structures. It applies to anything to do with physics. If you were to look at a lightning strike, or I'd actually encourage you to look at things like lightning sand sculptures. When a lightning hits the ground in a sandy structure, it melts the sand, and then the sand turns into glass, and you can actually remove that from the ground, and they're called sand sculptures due to lightning. All of these physical phenomena are doing exactly the same thing as nature is doing, which is minimizing the energy, looking for the path of least resistance while maximizing the transport efficiency. So the lightning is transporting electrical energy, current, from one domain to the other, or heat from one domain to the other, but it needs to minimize the resistance while doing so. And that results in structures that are very unique and very organic looking, even though they have nothing to do with biological structures. These are not organic in nature. These are two-dimensional or three-dimensional partial differential equations, basically. Yet, they look very similar to trees. They look very similar to lungs. And you can go on and on about these structures. At the end of it, it all comes down to maximize and minimize. You want to maximize what you want, and you want to minimize your cost. And the cost can be anything, energy, dollars, anything that you have to pay for that you don't want to pay for, you need to minimize. And anything you want to benefit out of it, you need to maximize. And the fractals are perfect geometries for this. So it didn't take engineers long to figure out how to take these information and use it and apply it to engineering designs. What you see up here is a two-dimensional fractal heat exchanger from Oregon State University. You start from a central distribution point and ever-decreasing diameters of heat channels. And at every junction, you're bifurcating into two while minimizing your R ratio, also maximizing your surface distribution. So this is an example of a thermodynamics problem. What else can you do with it? Anyone with a cell phone, if you were to see your cell phone antenna, you're going to see that those are actually Karpinski triangles most of the time. Why? Because you're maximizing the surface area given an amount of surface area. You can actually put, theoretically, very large surface area in a equilateral triangle by ever decreasing your triangle ratio. So in engineering structures, what costs us money is energy and weight, size. And what we're trying to maximize is efficiency and effectiveness. Our engineering processes are never 100%. There's no such thing as perpetual motion machine. We're always dealing with efficiencies that are anywhere from, as low as 10% as high as 98%. So that we're always losing some of the energy, but we're trying to maximize it so that we can get the most benefit out of it while minimizing our cost. So I'm going to do a very quick, as a shameless plug here for my company, Raytheon Corporation. It's based on 4 divisions, and Raytheon Corporation became a company by Virgin United Technologies Corporation and Raytheon. My company here is Collins Aerospace. Our motto is anything that flies, we're on it. From the next couple of slides, you're going to see that we do anything from the systems point of view that goes into either fixed wing aircraft, or rotating wing aircraft, for commercial or military. And our sisters company, a few minutes down the road, is Pratt & Whitney. And there, we make the engines, either for the military market or for the passenger jet market. I work with both of these divisions very closely, but my parent company is Collins Aerospace. And in Collins, we have 6 major divisions. So anything from structures that carry load in sense of mechanical engineering to software, to electronics, machinery that controls load path within the aircraft, or electronics that control the machinery is our domain. And my division is the power and controls. Within the power and controls, we have a few different subsectional business units. The one that I report to directly is called air management. This is the thermodynamics end of it. In air management, we all fly. So when you are up in 30,000 feet, you still want 70 degrees Fahrenheit or 20 degrees Celsius inside air when it's minus 40 outside. Or when your jet engine, is reaching temperatures that are higher than the metal melting temperature, you still need to be able to control and dissipate that heat out of the atmosphere. So that's the end of your work in air management. Specifically heat exchangers. What is a heat exchanger? Like I said, none of the engineering methodologies are 100% efficiency. So we are going to use some of the energy we input as parasitic energy. And this is very evident in heat transfer. Like in your car, for example, you have an internal combustion engine, unless you're driving an electric car. Your internal combustion engine is at most 30% efficient, right? So 70% of the energy you get out of burning the gasoline or diesel inside, you're going to have to dissipate because it's not useful energy. And you will have a radiator inside your vehicle, and that will be an air-liquid type heat exchanger. So the liquid will take the extra energy out of the engine, push it through the radiator, and the flowing air will dissipate it into the atmosphere. Air would be more of aerostructures type applications where you're in an aircraft and the engine is generating a lot of heat, and that heat needs to be dissipated. So inside the engine, you have combustion air. Outside the engine, you have the cold air coming from the airflow. You mix them, not by touching, but one goes through an internal channel of a metal structure, one goes through the external channel of a metal structure, and that thermal energy is dissipated. So this is the basic of heat exchanger. As far as the mathematical problem goes, it's very, very simple. But unfortunately, when you put it into practice, there are lots of problems associated with it. This is a traditional heat exchanger that we make for the passenger aircraft market. And if you look at it, you see that it's designed by an intelligent being. It's designed by a human. Why? Because it's periodic, it's uniform in structure, it's manufacturable. So it takes a lot of the criteria that humans like. There is order in the structure for us to design it. And it's also easy to manufacture. And it serves a purpose. And it's very efficient in transferring heat. So the hot air will go in through these ports here, we call the inlet manifold. And it will go through either this side or this side in various configurations. And as the aircraft is flying, the cold air will come from the front face and it will pick up the heat from the hot flow, and it will get dissipated from the back here at the exhaust of the engine. So the structure itself is, but there's a huge problem with it, and it's prone to thermal failure. Why do we have a thermal failure issue on a heat exchanger? Well, we start looking at the requirements for the heat exchangers. This is a picture of a F-35 engine that you make at Pratt & Whitney. We're dealing with various requirements. One is there are a certain amount of heat you need to dissipate out of the engine and put it in the airstream. There's also efficiency requirements, and they're given in terms of pressure drop. Nothing is free in physical processes. If you're flowing a medium from one of these ducts coming out of the, one of the engine sections and going to the other engine section through a heat transfer mechanism, you are going to lose some of the energy. Because a fluid is flowing through a medium, flowing through a geometry, you're going to lose some of that energy. And that's called the pressure drop. We need to minimize this because pressure inside the engine, which is energy, is precious. Minimum pressure drop means more flight miles you're going to get out of the fuel. Also, we need to minimize weight. Anything that flies, there's a huge penalty associated with heavy structures. So we need to minimize the weight as much as possible. On top of that, everything goes down to, dollars and cents. How much this structure is going to cost based on manufacturing cost, based on material cost. You're dealing with temperatures that are really, really high. And when the temperatures are really high, you cannot use traditional materials. So now you get into exotic alloys, like, high nickel alloys, where the cost becomes a really big issue. We are well beyond titanium's capability, and we're dealing with nickel alloys. And the problems are going to be low cycle fatigue, high cycle fatigue, and damage tolerance. Low cycle fatigue is thermal stress. When you start the engine, you're starting from ambient condition. It could be in, Alaska, minus 50 degrees, or it could be in Arizona, Phoenix, 120 degrees. When the engine starts, it's going to reach the temperature very, very quickly in a matter of seconds. So now you have this huge transient heat cycle, and your temperature distribution throughout the engine is going to be varying. Because of that, you have thermal stresses. That's your low cycle. When you start flying, or when you're running the engine, you have vibration requirements. Core of the engine is not 100% balanced, so there's always some vibration coming from the rotation of the engine. And there are all kinds of other components, gearboxes, pumps, and etc. They generate their own pressure pulsations or periodic vibrations. And on top of that, there is damage tolerance. Nothing we make is perfect. There's always going to be some damage, inclusion associated with the structure. It could be, tiny cracks coming from the manufacturing defect, but we need to make sure that that tiny crack is not going to grow during operation, either because of fanning requirements or because of vibration requirements, and that we can manage that damage coming from this initial crack. So the physics of the problem is simple, but applying it to practice is very difficult because of these conditions. So biggest problem is the LCF. LCF stands for low cycle fatigue. Low cycle in terms of thousands of cycles. So the engine turn on and off will be in a few thousand cycles, while the vibration, high cycle fatigue, is going to be in many millions, if not tens of millions of cycles. What you see on the left is a magnified displacement field coming from a thermal cycle applied to a very simple, tube-type heat exchanger. Our heat exchangers look different than this, but the physics is the same. You have a varying temperature field, and you have boundary conditions. Based on this, we're going to end up with a stress field. We need to make sure that stress field does not cause fatigue failure, and that is the low cycle fatigue element. And since these temperatures are also very high, well above 1,000 degrees Fahrenheit, your material capability is also going to decrease quite a bit. So we have to take all of these into account, design a heat exchanger that is minimum in weight, generate stresses that are minimal, and easy to manufacture, and is low cost. So welcome to fractal heat exchangers. So this is a drawing from one of the patents I received on this, fractal heat exchangers. I believe there are up to 15 of them now in various different configurations. Why fractals are very appealing? Well, you can also immediately see that the surface topology is smooth. Just like nature, there are no sharp corners here. And if you are dealing with stress problems, you know that sharp corners generate stress concentrations. Stress concentrations lead to crack initiation and crack propagation. When you eliminate sharp corners, you're actually reducing your fatigue probability dramatically, and you're increasing your survivability also dramatically. On top of that, geometries like this, where you have bifurcations coming in 1 to 2s or 1 to 4s and 1 to 8s, they increase your, they decrease your stiffness quite a bit, and they also increase your resistance to surface stresses dramatically. So you're getting two birds. What we've seen in practice, in simulation and in testing, geometries like this actually end up, compared to the traditional heat exchangers, with surface stresses almost as low as 1/10 of what we used to, which are those rectangular-looking plate and fin type heat exchangers. And that's a dramatic difference in terms of fatigue capability. And also, since these structures are optimized for flow, we are actually reducing a lot of the pressure drop requirements that are coming from the customer. But there are challenges associated with it. What are the challenges? The main challenge we deal with it is these are very non-traditional geometries. If you ever work with a CAD software, be it NX or CATIA, Pro Engineer, SolidWorks, it's easy to generate geometries using extrusion sweeps, variable sweeps, and etc., using the bare bone geometrical entities. When you deal with structure like this, it's a completely different story because CAD programs are not designed to generate organic structures. They're designed to generate periodic, repeating, simple structures. So how do you take a structure that requires variable cross-section thickness, because you don't want to have uniform cross-section thickness that will increase your mass while giving you nothing in return? You need G1 and G2 surface continuity. G1 means your surface tangents are going to be identical at every bifurcation point. G2 means the second derivative of the functions, which are your surface curvatures, are going to be identical at every point. And also, you're going to have several layers of bifurcations. How do you generate geometries like this using traditional CAD tools? Because if any of you work with big corporations, it's almost impossible to go to IT department and say, hey, I know we have graphics and whatnot, but I need this software package. You're not going to get a yes answer. You need this. And with this, we've actually generated automated design tools within our CAD system, and we use Siemens NX as our CAD base, at least in my division. In Raytheon Technologies, we basically have everything. We have access to all packages, but my division, we are using NX. And what you see on the screen is called Realized Shape. Realized Shape Engine is a free-form geometry tool. I traveled to Poland for this particular application, and we have a lot of smart people there as well, mathematicians in our division. And we wrote this software package that plugs into NX and generates these fractals for us in a matter of seconds. It used to take me days to put these geometries together. By automating it and putting it in software, now we can do it as you see in real time on the screen here. The problem with Realized Shape Engine is that it is not parametric. So there is no drawing for this. You cannot generate a drawing and send it to your manufacturer. It's only going to live in 3D. And if you need to change some of these dimensions here, you need to regenerate the geometry from the beginning. Because of this, we also generated parametric engines. Now, there are advantages and disadvantages using Realized Shape Engine, which is free flow, or parametric engines, which are tightly controlled dimensions. Realized Shape will give you anything you want. There is no limit in what you can create. Parametric engines are constrained in what you can create, but they are tightly controlled in dimensions. So we use both and combinations of both. And what you see here is a resultant coming from a parametric engine. It's driven by an Excel spreadsheet. All we have to do is put our dimensions and click a button, and Siemens NX will give us a new solid geometry in a matter of 2 to 3 minutes, depending on the complexity of this parametric shape. So because of this, now we can run parametric optimization studies using computational fluid dynamics or finite element analysis, and we have done so. We've optimized a lot of these parameters because tools like this automate the geometry generation process. And we generate these things in simulation. The reason for that is alternative is going to be actually manufacturing. We do that as well, but it's going to be only additively manufactured. In Collins and Raytheon in general, we do have quite a few dozen laser sintering machines. And since these are high temperature alloys, nickel, Haynes 282 to be specific, these are going to be in high demand. So being able to go to a laser sintering additive manufacturing machine, there's a backlog. As much as you can do in simulation within a reduced your development time. So we use star CCM class of fluent for the computational fluid dynamics. And then from those conjugate heat transfer time domain solutions, we'll take those temperature values, map it to solids, and then that goes into either AVIX or ANSYS for transient thermal stress analysis for low cycle fatigue. And then the same geometry will go into high cycle fatigue vibration studies, again, in AVIX or ANSYS. You can do the same thing in NatStrand if that's what you have. Theory is exactly the same, but it's a repetitive process, and automated geometry tools make it possible. I'd like to spend a few minutes talking about Murray's law. So this was developed in the early 1900s. Cecil Murry is the person that developed this generic equation because it was evident that there is a relationship between the bifurcation radii in either air transport systems or blood transport systems in biological entities like humans or animals. So there's got to be a physics that governs why the ratio of your lungs is bifurcated, reduced by a certain amount, or ratio of your veins in your cardiovascular system reduced by a certain amount. After this study, it was found that the magic ratio is 3, n equals 3 for laminar flow in a closed system. So if you're transporting blood, and if you're transporting air, and if you were to look at different animals, this could be as large as the blue whale, it could be as small as, your garden variety mice. And if you were to look at their cardiovascular system bifurcation R ratios, it's going to be more or less 3. It holds from small structures to large structures. So initially we started with n equals 3. But we're not dealing with structures that are laminar flow, and we're not dealing at room temperature, and we're not dealing with structures that are well-behaving and low velocity. So our structures, we're dealing with very high temperature. On top of that, our flow is not necessarily laminar. We do have turbulent regions, and in certain cases, proprietary information, we create turbulent regions in certain geometries so that we increase the heat transfer ratio. So we're not dealing with laminar flow. Our velocities are very high. We're reaching not quite Mach, but definitely over 0.5 Mach in these heat transfer flows. And our pressure is very high. So for the air coming in is going to be at very high temperature, very high pressure, and very high velocity. We use simulation to figure out what our magic ratio is. And our magic ratio is not 3, but it's something lower than 3 and something higher than 2. And it works best for aerospace applications. And because of this, and because of using fractal applications, we've been able to mimic nature. In doing so, we actually reduce our structure weights. It increased our pressure capability. We are taking full advantage of additive manufacturing because these geometries, there's no way you can generate it using subtractive machining techniques. And we have a dramatic decrease in our pressure drops. It's because these structures are generated using optimization techniques for flow applications. There are some future challenges we have to deal with. The first one is the next generation engine that's going to go into the F-35 Joint Strike Fighter. We have to increase the temperature to make it more efficient, which means that we're going to have to be a lot more heat dissipation that's going to be required for exactly the same airframe. And we have to pack more efficiency into the same exact volume. So we're going to have to get smarter and imitate nature with even higher fidelity for the next generation engine for the F-35. Very quickly, talking about bypass ratios. I mean, I know that this presentation was at Ohio Aerospace Institute, so this is probably preaching to the choir, but for those of us who are not familiar with aerospace or jet engines, there's something called bypass ratio. And the bypass ratio is how much of the flow goes through the engine core and how much of the flow goes outside the engine core coming from the turbine blades. Here you see one of our engines, the Pratt & Whitney geared turbofan engine, bypass ratio, which means most of the air coming inside of this engine nacelle will go around the engine. A little bit of it goes through the engine core. This is where the energy is generated, but this is not where the propulsion is generated. For commercial airliners, propulsion is generated in front of the engine with these large engine turbines. If you look at the military engines, on the other hand, you see that the front turbines are pretty much the same diameter as the rest of the engine. Why? Because military engines are designed for supersonic flight, and they require very low bypass ratios, very small bypass ratios, and they generate very high thrust for the given volume. But the price you pay is fuel consumption. For the passenger aircraft engines, you use very large bypass ratios, you fly subsonic, and the benefit you get out of that is going to be lower fuel consumption. And the price you pay is the speed. So then how are you going to combine these two? This is the holy grail of engineering right now in aerospace. That is being able to generate a bypass ratio when you're cruising, and then bypass ratio to a lower bypass ratio when you are engaged in military flight. Welcome to the next generation engine design. And that is the adaptive cycle engine with the third stream. Here we are taking the higher bypass ratio and lower bypass ratio benefits and adding it to an engine that has three streams, not just high, low, but there's a middle engine stream that it can either be assigned to a higher bypass or lower bypass based on the mission profile. This is generating an exponential increase in thermodynamic complexity for us. It's because that's just one part of the aircraft design. The other part of the aircraft design is going to be a reduced heat signature, lower weight, increased fuel efficiency, and it's going to be even stealthier than the fifth generation fighters like the F-22 and F-35, which means the heat signature you put in the atmosphere has to be even lower than what we have today.
This is Carol. Oh,
yes.
Listen up.
There's a question?
There is, we'd love to stop at this point. I know.
Okay. Actually, this is the last slide.
Oh, well, then we did all right. Keep going. And
This was the sixth generation fighter, our biggest challenge. And here I will stop and I'll take some questions and hopefully I can answer them.
Thank you. At least for me, your explanation of some of these engineering principles and physics was wonderful. I appreciate that very much, Ahmet.
Thank you very much.
First, I'm going to see if anyone in the audience has a question or a comment, and then I want to introduce Em, who is taking the place of Britt, who is now monitoring the chat. So we'll get some thoughts or comments from online.
So I just have a comment. I did a small-scale study on the reversion canals of interstitial fluid found in the cortical bone of humans. And what happens in there is we see that there's mixing occurring within laminar flow. And I just was like, this got me really excited about maybe you guys can run with this or have thoughts on some of this. I don't really have a question or anything, but I thought...
Wait a minute, you got to say that all again.
Okay.
That didn't sink in.
Okay, so in the human cortical bone, there's...
Okay, that's in your ear?
No, human cortical bone is in the femur.
Cortical bone. Okay.
Yeah, so it's in the femur, and they have these canals called the reversion canals. And what happens is there's interstitial fluid that flows throughout the system. And as we walk, we load, and the flow goes down, and then when we lift our legs up, the flow goes back. And so interstitial fluid flows forward and backwards, but there's mixing that's happening in these canals. And it's laminar. So I haven't really fully conducted the research on it, but I just thought this is an interesting concept that someone could run with, or just a hypothesis or connection that you could potentially run with this.
Nice.
So yeah.
All right, thanks.
So when you run that research, you're actually going to see that those are load sensing mechanisms. Human bones are actually sensing the load, or any skeletal structure, as you are loading it. And if you're not using that particular part of the structure, that structure gets removed. And if you're using a certain parts of the structure, that structure gets densified. That's why, like the astronauts in space, they move, right? So those are actually load-bearing structures. We are trying to imitate things like that. It's a fascinating topic. It's active monitoring, basically, in nature. So thank you for that comment.
All right, Em, do you have anything going on online? Oh, you have a microphone there. Just hit the red. Okay.
Hi, sorry, I'm kind of jumping in the middle of something, so I hope that I'm getting this correct, but I have a question online that says, or at least a comment, coming at this from a totally different world, surface water pollution, but could likely use these types of designs to provide increased filter media contact with stormwater to remove nutrients and pollutants. And then a comment later saying, any chance Ahmet can create something?
Yeah, I mean, that's a really interesting question. Fluid mechanics is not my specialty. My specialty is solid mechanics, but I would strongly suggest studying diatoms for that. How do you increase your surface area for the given cross-sectional area so that you can capture most of the pollutants? I think there's a link there. I just don't have the answer for it.
Peter?
Thanks for the talk.
Sure.
Just a quick question. So when we work with companies in engineering, often engineers tell us, well, we work in high pressure, high temperature systems. Biology really has nothing to offer us. So we hear that all the time. But if you could, with one thing, change the way in which we train biologists and engineers at the university level, what would that one thing be? What would you do that we could conceivably do to make this broader, more broadly understood and investigated?
Too high is a relative thing. I would give examples of too high from nature. If you were to look at an engineering structure, 25,000 Gs would be incredibly high, wouldn't it? Yet, an American red-headed woodpecker will generate 25,000 Gs every time it hits a tree. And it's handling it perfectly fine. So, dismissing the designs coming from the nature, I think, is a huge mistake based on the physics dimensions. What we are seeing, so it's not one thing, maybe it's five things now. But we are seeing from our experiences is all it does is it changes the topology a little bit, but the fundamental shape of the topology remains the same. You're changing the dimensions by maximizing for the next order physics, while the overall topology remains very, very similar to lower order physics. So I would not take that as an answer. We are seeing exactly the opposite in our application. And I'm not aware of any other structure that's going to higher temperatures than we deal with when we have, say, re-entry into the atmosphere.
So, Ahmet, would you suggest that engineers be required to take a biology class?
This is actually a really interesting question as well. When I was teaching at Rochester and Yale, a lot of my students came from the biomedical and biomedical engineering and biomechanical engineering. So there's a very tight-knit information exchange that goes on between mechanical engineers and the biomedical and biomechanicals.
Okay.
You should take that course. Absolutely. But it's both ways. You should also make your biomechanical and biomedical engineers take mechanical engineering courses as well, because that two-way communication works.
All right. Thank you so much, everybody. Thank you, Ahmet. Let's give him a hand.
Thank you so much for listening.
Nice.
Okay.